Hello and welcome to the presentation for the paper A47 F² per bit chart sharing based sequence-dependent PUF with a permutative challenge. My name is Kai-Uwe Müller and this work is done together with Alexander Stanitzky and Rainer Kokocinski at the Fraunhofer IMS in Duisburg in cooperation with the University of Duisburg-Essen as part of my dissertation work. At first, we will have a look on the motivation and objective. We will describe physical unclonable functions in general and how they can be used for authentication purposes. Then we have a look on the performance metrics for these so-called PUF. The second part is the concept and design of a novel analog PUF architecture, where we will have a look on the actual device mismatch, then the modeling of the challenge response behavior, and the actual key generation to have a cryptographic key. The third part is the Cmos implementation, where we show the design in a Cmos technology of the Fraunhofer IMS called L035. We will have a look on the measurement results for these PUF and evaluate them with the performance metrics. Basic motivation is that we want to perform a secure authentication in resource-constrained embedded systems, which may be an IoT device that has a sensor on it, and usually these nodes don't have a crypto processor or another high-performance processor implemented, so they can perform any cryptographic calculations. You have low power requirements, maybe because it's battery powered or solar powered, and you also should have a low area usage so that you can produce a low cost device. What can be used for this purpose is a so-called physical unclonable function that has some inherent properties that are implemented or present from the actual device fabrication, possibly in a semiconductor device fabrication. These values can be capacitor values that differ from one device to another one, and basically these properties are uncontrollable. So if you produce another device with the same layout, it will always get a slight variation from the first device that cannot be controlled by the actual fabrication process. Usually you use a so-called challenge response protocol, so you send a challenge to the device and it gives you back a certain response to this challenge. All challenges can be collected by a server, and then you can authenticate a device by performing this challenge response operation, compare the response to the original stored response, and if it's the same, the device is authenticated. Our objective now is to find a novel lightweight strong PUF architecture that can be implemented in a regular Cmos process and that exceeds the strong PUF requirements in terms of the number of available challenge response pairs, which is also called the challenge response space. Generally, strong PUF at least have to have a challenge response space of 2 to the power of n, where n stands for the number of individual elements. But strong PUF also have to hold some basic performance metrics, which are the uniqueness. This is defined by the Hamming distance between different PUF for the same challenge, and the reliability, which is the Hamming distance between multiple readouts of a PUF for the same challenge. The basic idea now is that we have a switch capacitor circuit that consists of n stages. On the left side we see an example with 3 stages. We can see that every stage consists of a set of static capacitors called Cp and Cm and one reference capacitor called Cref. In the initialization phase that is happening first, the static capacitors Cp and Cm are just connected in series and all stages are connected in parallel to each other. If we now do the initialization phase, we close the init switches that are shown on the left side and connect the Cref capacitor to a DC voltage source, which then charges the capacitor to a certain charge value. The initialization phase ends and the init switch is put back to its original position, but the charge is remaining on the reference capacitor. Second, the switch S1 is put into the other direction so that the reference capacitor is put between the CP and the Cm capacitor. The charge that has been on the capacitor, on the reference capacitor, now is shared into between all capacitors in the network. And what you see on the amplifier inputs is basically a voltage step. If this charge sharing procedure has ended, the second switch is flipped, so S2 in this case, and then afterwards S3 is switched. Every time we put in a reference capacitor, the topology of the whole network changes. This means that also the input capacitance that can be seen by the reference capacitor is different for every stage. Even if all reference capacitors have the same value, the voltage steps are different from each other because of the stages that already have their reference capacitor put in or not yet put in. We can also see this on the equation where we have the final output voltage, which consists of a sum of voltage steps, which themselves consist of smaller sums which are dependent on all other stages. We have a sum from k equals n plus 1 to n, so all stages right of the actual stage which just have Ck, so a series connection of Cp and Cm, and all stages left of the actual stage from k equals 1 to n minus 1, which is a series connection of Cp, Cref and Cm. If we now get back to our definition of PUF and have slight variations between the reference capacitors, for example, we can change the permutation of the switching sequence. So we can decide if we put in C1 first or C2 first and so on. We have a faculty of 3 different possibilities to put in these reference capacitors. On the right side, we see this for an 8-stage topology where we have a faculty of 8 different challenges, so about 40,000. And we see that the voltage outputs are different for every challenge, which is the permutation of the switching sequence. On the bottom, we see the histogram of these values. So we see that we have some kind of normal distribution of the values that we can later use for a key generation process. To model the challenge response behavior of the PUF, we have to have some information about the variation of the actual devices, in this case the capacitors that are used. Therefore we use so-called Paragram's law, which defines the standard deviation of the capacitors that are used in % of their actual size. And this equation uses some parameters which are AC. This is the Paragram parameter that is defined by the actual technology that is used and usually provided with a PDK of this technology. And we can choose the area of the device, length by width, in this case capacitor area, but it can also be a gate area for transistors, for example, where a smaller area gives a higher mismatch and therefore a higher standard deviance of the device, and also later for the voltage outputs. And what we also can choose is the ratio of the static capacitors to the reference capacitors, which is later chosen to be R equals 8. So the ratio is static capacitors are 8 times larger than the reference capacitors. And therefore we can choose the reference capacitor as the smaller of the two ones to be minimum length and minimum width to have the largest possible standard deviation. We now have a bunch of analog values as the challenge response behavior, but what we actually want to have is some bit sequence that can be used as a cryptographic key, for example. What we now do is a basic key generation method that is also used in ring oscillator PUFs or, for example, other analog array PUFs, where all possible analog values are arranged according to their size and given a new naming called the index from 1 to, in this case, 32,000. Now the pairs are built out of elements that have a maximum distance to each other. What we already see with this arrow, with this black arrow, is that we build, for example, a pair of index 1 with index 16,001, and then go on with a pair 2 with 16,002, and so on. This makes us sure that we have all possible pairs covered and they all have the maximum possible difference, analog voltage difference to each other. To now build an actual bit value out of these pairs, we compare the original challenge IDs to each other. This is the challenge for, if the challenge for index 1 is larger than the challenge for index 16,001, then the bit is built out of the Heaviside function of V1 minus V16001, where the Heaviside function is 0 if the value is lower than 0 and 1 if the value is larger or equal to 0. On the other hand, if the challenge value or challenge ID of the index 16,001 is smaller than the one of index 1, then the bit is built of the Heaviside function of V16001 minus V1, so the other way around. We did an implementation in the L035 process, which is the in-house 350 nanometer process of the Fraunhofer IMS in Duisburg, where we implemented different capacitor types for the network, which are the poly-poly capacitors with a size of Cref equals 25 femtofarads, which is the smallest possible value regarding the area constraints. And then we have implemented some slightly larger capacitors, which are also poly-poly capacitors with Cref equals 200 femtofarads. Then we also implemented some MOS capacitors with a size of 150 femtofarads, which we see on the right side. That are also done in some meandering fashion. So the active area is meandering throughout the device. So we have a larger errors because of the edges maybe, and therefore a larger mismatch of the devices to each other. So a larger random mismatch. The ratio is chosen to be R equals 8. That means that Cn and Cp are sized 8 times the Cref capacitors. The implementation is also done with different switch types, which are standard PMOS transistors with a W to L ratio of 2:1, and the transmission gates with a W to L ratio of 20 to 1.2 micrometers. The block diagram of the Asic implementation is shown on the right side, where we have the block permutation control that calculates the permutation, actual permutation out of the input signal, which is here called cell, so select, which is the actual challenge that we put in as a binary value. And then the actual permutation that corresponds to this value is calculated in the block, and the PUF is controlled also by this block. So what we have seen earlier in the timing diagram, the switching process is done actually by this block. Then we have the actual PUF block on the right side to this, which has these differential outputs that are put into the output buffer, which is an instrumentation amplifier that has a small input capacitance. And then the values are put out through a multiplexer to the chip outputs. We have also some other blocks on the design, which are some basic biasing for the buffers and an oscillator to have a clock signal. But also in this case we have implemented a RISC-V processor to have a possibility to control the PUF and also to perform the key generation that has been mentioned before. But this is an optional module that not actually has to do with this PUF design, so we don't have a deeper look onto this. On the left side we see the actual produced IC, where we have on the bottom the 6 different PUF arrays we mentioned before, with different capacitor modules and also different switches that are used, where on the right side these 2 arrays are exactly the same, so we have some arrays that are comparable to each other. We now see some measurement results for the test chip in this process, where we see block 4 and block 5, which are the MOS capacitors we mentioned earlier, and the small PMOS transistors as switching devices. We have measured 10 different ICs for these PUF and plotted all analog response values for these PUF. We see that they differ a lot from each other, from block to block, but also from IC to IC. That's a good thing because we want to have high uniqueness between these devices. But what we also see is that we have a relatively small maximum signal amplitude of about 3 millivolts between the highest and the lowest possible response value. But we use this key generation method we described earlier, and therefore these maximum differences are enough to be read out by a analog to digital converter, for example. After performing the key generation, we compared the generated keys to each other and measured their Hamming distance to each other. So this is the inter-Hamming distance, so the uniqueness for unique challenges, which means that we build the key generation on each individual IC and build a key out of it, and then compare all bit strings to each other in terms of their Hamming distance. There we have a mean of about 48.5%, where 50% would be the optimum we want to achieve, to have every key string differ to another key string by half of their bits, and the standard deviation is about 6.5% in this case. What we did second is not to perform the key generation on each individual IC, but to perform it on one IC, store the actual pairs that are found and used, and use them to evaluate another IC with the same pairs and to build a key out of them. This is more important of a unique feature, because every time you want to perform an authentication on one device, you don't want another device to give out the same results. So this is the basic uniqueness parameter here that is shown here, and there we have a mean of 44.5%, where again we want ideally to achieve 50%. So this is a bit less, which means that we may have some systematic variation that is present in all devices. And we also see some standard deviation of 13%, which is also a good value for this metric. The next thing we want to have a look on is the reliability. In this case, we measured all analog values of one device in 3 different ambient temperatures, which is -35, +20, and +85 degrees Celsius. There we see already that the mean value differs a lot between all these devices, and it seems to be not reliable at all. But because we have a difference pair building algorithm, we can just have a look on the actual so-called detrended values, where we removed the mean value out of these values. This is shown here, and there we already see that the behavior is much closer together between all these values. And if we now perform our key generation we did before, we have a maximum bit error rate of about 1.3%. So this is basically very small error between the multiple readout at different ambient temperatures. And this is sufficient if the uniqueness is always higher than this 1.3%. As conclusion, we can say that we found a novel PUF architecture that can be called lightweight, because we extended the number of challenge response pairs that are required for a strong PUF of 2 to the power of n to a value that is for larger n much higher. It is then faculty of n divided by 2, where the 2 comes from the pair building and the key generation algorithm. The implementation size we measured is only 47 f² per bit, where f is the feature size of the technology used, in this case 360 nanometers, which is much smaller than most other implementations. We have a good performance in the evaluation metrics we defined before. We have a uniqueness for unique challenges of 48.5% in average, and a value of 44% for the universal challenges. We also have a high reliability with a maximum bit error rate of 1.3% measured in 3 different operating temperatures.